My name is Johannes and I am a chemistry student in the group of Professor Patrick Teato and Pavel Levkin.
I'm Maria. I'm a PhD student at the group of Pavel Levkin and I'm a member of the cluster 3D Matter Made to Order. I'm also a holder of Carl Zeiss Foundation Scholarship.
Together we would like to answer a couple of questions to our recent publication.
Our publication is about using liquid wells to confine other liquids as an alternative to solid vessels. We show the unique properties that a liquid wall has, such as self-recovering or the ability to extract substances from one liquid to another.
Liquid walls are 3D barriers made entirely from water, which is confined on a certain place on a surface, which we can see here in this profile view.
When a liquid forms a closed ring-like structure on the surface, it can become a physical barrier for another liquid and confine it inside. In this regard, it behaves exactly like a glass beaker that prevents the liquid inside from spreading all over the surface.
The water is placed on a water-loving area. We chemists call this hydrophilic. It is surrounded by a water-repellent area, which is hydrophobic. So, because the interaction of the water molecules with the water-repellent surface is so poor, the water molecules prefer to interact with each other, even acting against the force of gravity. And as a consequence, the water does not spread over the surface, but is instead piling up on the hydrophilic area. So the water-repelling and the water-loving areas are modified with a certain surface chemistry that is either very similar to water or very different from water. So in the water-loving or hydrophilic area, we have functional groups on the surface which are very similar to a water molecule. Whereas, on the contrary, on the water-repelling or hydrophobic surface, we have a surface chemistry that resembles that of an oil, indicated here by a long carbon chain.
Of course, it can mix with some liquids. If the liquid generally mixes with water, it won't be able to be confined inside. For example, regular alcohol will spread and mix with water. But olive oil or mineral oil will be able to stay confined. The first step to prepare such a system is to modify the glass substrate. For that, we create water-loving and water-repellent areas by shining UV light under the photomask to create the desired pattern. After the modification, the glass substrate is still transparent because molecules are too small to see, but if you spread water on the surface, it will self-assemble in the shape of the pattern. Then the last thing which is left is just to pour the other liquid inside.
Liquid walls could serve as compartments for the pharmaceutical industry for miniaturized chemistry. In those processes, thousands of compounds need to be synthesized individually, and since the water walls can be rinsed off and reformed, the containers can be reformed and for that reason economically recycled.
You can also check our paper at the source publication, and if you are interested in fascinating applications of surface chemistry, you can check our group website.